Hello and good evening, everyone. My name is Irman Haikal bin Irwan, student ID MA23093. I'm from Group 3. Today, I'm going to present to you about lab air conditioning. First thing first, for the introduction, the purpose of air conditioning is to enhance indoor comfort by treating air. The process involved is sensible heating, which raises air temperature, humidification, which add moisture, and last, cooling and dehumidification, lower temperature and remove excess moisture. For the combined approach, used together to achieve ideal indoor condition, especially in hot and humid climates. The working fluid for air conditioning is R134A. The thermodynamic process involved is isentropic compression, constant pressure heat rejection, isentropic expansion, and constant pressure heat absorption. For the objective of this experiment, first, to research the air conditioning system part. Second, to look into how the air conditioning system fan speed and air temperature and relative humidity relate to one and another. Last, to calculate the air conditioning system coefficient of performance (COP) using the operating fan speed input.
Hello everyone, my name is Muhammad Haziq bin Makropi, Matric ID MA23087. Now, let us move into the theoretical framework. Our experiment is grounded in the first and second law of thermodynamics, which are fundamental in analyzing the behavior of the energy within any system. The first law, also known as the law of energy conservation, state that energy can neither be created nor destroyed. In, in an air conditioning system, this means the electrical energy supplied to the compressor is transformed into mechanical work, which then facilitates heat transfer from the inside space to the outside environment. The second law of thermodynamics deals with entropy, the measure of disorder in a system. It tells us that in order to move heat from a cooler indoor environment to a warmer outdoor environment, we must supply work. As a result, entropy increase. This helps explain the inherent energy losses and irreversibilities that reduce overall system efficiency. The refrigeration cycle includes four stages. First, compression. The refrigerant vapor is compressed, then increasing its pressure and the temperature. Second, condensation. The refrigerant then releases heat to the surrounding and turns into a high pressure liquid. For the expansion, the liquid passes through the expansion valve, dropping in pressure and temperature. The evaporation, the low pressure refrigerant absorbs heat from indoor air, cooling the space. As example, we use R134A as the working fluid, chosen for its favorable thermodynamic properties and environmental compatibility.
My name is Muhammad Irkasua bin Ibu, Laboratory MA23144. I will explain about experiment of a conditioning laboratory unit. It has quite part. The first is evaporator. This makes the air cooler and the fan blows this cool air back into the room. Next is condenser. This part releases heat to the surroundings. Makes expansion work. It controls the flow of refrigerant. The hygrometer is measure how much refrigerant is flowing. The last is compressor, which pumps the refrigerant through the system. Next is experimental procedure. The first one is ensure the air conditioner power source is properly connected and there are no burn edges. Second is check that all measurement device, sensor, humidifiers, thermometer are working correctly. Next is turn on the main power switch. Next, start the fan and refrigerant unit to begin cooling. Next, set fan speed to 50% and record air temperature, refrigerant temperature, and pressure at T1 to T5. Next, increase fan speed to 100% and take the same reading at T1 to T5. Next, record the refrigerant flow rate from the flow meter. Next, slowly return our value, temperature and pressure to starting levels. Next, turn off the fan, refrigerant unit, and reset fan speed to zero. The last is finally switch off the main power to shut down the unit.
Hello, my name is Muhammad Arif bin Muhammad and my message number is MA22048. Today I will explain about the result. So, firstly, for the result, we take the refrigerant temperature, air temperature, enthalpy, and entropy. For this experiment, we use 50% fan speed and 100% fan speed. So as we can see, at 50% fan speed, the COP was 0.1808, which indicate the better energy efficiency. When we increase the fan to 100% speed, the COP was dropped drastically to 0.0673. This decline shows that the higher airflow rate do not always mean the better performance. In fact, they can lead more to the energy waste. So from our experiment result, we observe a clear relationship between fan speed and the coefficient of performance, which is COP, of the air conditioning system. As the fan speed increase, the COP tend to decrease. This is because while the higher fan speed improve airflow and enhance the heat transfer, they also increase the power consumption of the fan motor. When the added energy usage outweigh the thermal benefit, the overall system efficiency will drop. However, reducing the fan speed too much can also impair heat exchange. Therefore, it is important to strike a balance using a optimal fan speed that maintain the effective airflow while minimizing the energy consumption to achieve the best system performance. Okay, this slide highlight the relationship between the fan speed and the enthalpy value in the air conditioning system, which is directly impact on the cooling efficiency. At 50% fan speed, the enthalpy difference between zero point 0.1 and zero point 0.4 is 5.93 kilojoule per kilogram. At 100% fan speed, this difference slightly decreased to 5.36 kilojoule per kilogram. This reduction indicates that less energy is being extracted from the air at the higher fan speed. This suggests that a lower speed, the system has more time to absorb the heat from the air, resulting in the better cooling performance and more effective thermal exchange. Another key observation is sharp increase in H2 at 100% fan speed. It reaches 342.40 kilojoule per kilogram compared to the just 295.49 kilojoule per kilogram at 50% fan speed. This spike may point to overheating or inefficient heat rejection on the consider side. condenser side, which can reduce the system reliability and increase the wear on the component. Overall, the lower speed not only extract more energy from the indoor air but also help maintain the better thermal stability in the system. This reinforces the need to optimize the fan speed balance and airflow or energy efficiency. Okay, so this slide is discuss the impact of the entropy of the air conditioning system performance. So from our experiment observation, we found that as fan speed increase, the entropy of the air also increase. This rise in entropy lead to greater irreversibility in the system. In simpler terms, the system lost more energy that could otherwise be used for cooling. The higher entropy contribute to the inefficiency by increasing energy loss due to non-uniform air movement. This loss reduces the system ability to transfer heat effectively and ultimately lower the coefficient of performance. So while increasing the fan speed may improve the airflow, it also lead to higher entropy, which is negatively affect energy efficiency. This support our earlier conclusion that optimizing fan speed, not simply increasing it, it is essential for achieving for the best system performance.
Hello, my name is Muhammad Izufarman bin Zelishan and my ID metric is MA23090. So next, for the conclusion, the experiment successfully showed how fan speed affects the air conditioner's performance. We found that at 50% fan speed, the system had a higher COP of 0.1808, meaning it's worked more efficiently. But when the fan speed increased to 100%, the COP dropped to 0.0673. Showing low efficiency, the test also showed that fan speed changed the air temperature and humidity, with higher speed causing unstable temperatures and humidity. With higher speed causing unstable temperatures at different points. Based on the result, using a moderate fan speed gives better energy efficiency and more stable cooling. This knowledge can help improve air conditioner design and reduce energy cost in the future. So next, for the Q&A session, for the question 1, what was the main objective of this experiment? The main objective was to determine the coefficient of performance of the air conditioning system at different fan speed, and to understand how fan speed affects air temperature, relative humidity and system efficiency. For the question 2, why does COP decrease at higher fan speed? At higher fan speed, although air circulates faster, the compressor and system may work harder without enough time for heat exchange, causing more energy usage and reducing COP. For example, COP dropped from 0.1808 at 50% fan speed to 0.0673 at 100% fan speed. For the last question, which is question 3, what is the relationship between fan speed and air temperature? As fan speed increases, air circulates faster and may reduce air temperature slightly at some points, but also causes uneven or unstable temperature across TT1 TT4. So higher speed don't always mean better cooling stability. I think that is all from us, and thank you.